All right, section 6.2 is addition and subtraction of rational numbers. And there's a bit of background that we want to make sure that we understand as we're starting this. There's two different types of rational numbers that we could be adding together, two basic types. One is rational numbers where they have denominators that are already the same. And the other one is rational numbers where the denominators are not the same. So these are our two sort of definitions on this slide. Addition of rational numbers with like denominators. So if we have a over b and c over b, so they have the same denominator, and we want to add a over b plus c over b, we add the numerators together and the denominator stays the same. I'm going to draw you a picture of this in a moment so that you can kind of see why that has to work. The second one says if a over b and c over d are rational numbers and we're trying to add them, so the denominators are not the same, then I actually add AD plus BC over BD. I had a student teacher once upon a time that drew something that I thought was very clever, so I'm going to draw it for you as a visual aid for thinking about adding fractions with uncommon denominators. So she drew these X's, right? And she drew this and she said, we got a smiley face. So I thought it was a really nice visual to remember how this works. This AD is the first diagonal, A times D. The second one, BC, is the second diagonal, and then the denominator is the smile underneath. So it forms a very nice sort of image to keep in mind. It is not uncommon at all, however, for students to want to add the B's together here, for example. That would be a common gut reaction. I'm just add across the top, add across the bottom. Why won't that work? So one of the things to keep in mind is what fractions represent when we talk about part of a whole, like from the previous section from 6.1. So if you imagine drawing, I'll just draw a rectangular square here, but any whole image would work. You could do a pizza if you wanted to. And let's say that we wanted to shade in 1/3 of this. I didn't draw that well, sorry. Try that again. That's not great, but pretend. And I wanted to shade in 1/3, and I wanted to add another 1/3. So what I end up doing is I've shaded in 2, right? There's 2 pieces shaded, but each of them still has a size of 1/3. So I'd get 2 out of 3, right? There's 2 shaded in boxes out of the 3 boxes total, so the denominator stays the same because the size of the pieces stay the same. The reason we have to adjust on the bottom is because the size of pieces weren't the same to begin with. So I have to subdivide something, I have to change the sizes so that I can compare them in a way that creates equal quantities to be able to count. So so this one I did as an example was 1/3 plus 1/3. Let me give you another one down here, and I'll draw a picture and show you how you can think about it the same thing. We'll do the same 1/3, but then let's add 1/4. So according to our description over here, I should end up, if I make my smile face, with 4 plus 3 over 12, which is 7 over 12. That's what it says I should end up with. So how do I show that in terms of a picture? Well, I can draw that same rectangle that I had before, and I can make it into 3 slices. So you can almost imagine, cutting up a piece of paper, which you could physically do with children, or you could cut something much more interesting like a cake and do the same thing. So if you had 1/3 of this, you could shade in one of those 3 boxes, and that's fine. The problem is, how do you shade in an additional 1/4 when the boxes are size 1/3? So let me show you what you can do. You can actually take the same diagram and you can split it along the other side just because it's easier to split. Okay, I still have 1/3 of the whole diagram shaded in, correct? All right, so now how do I go about shading in 1/4? Well, 1/4 should be, oh, I'm sorry, I didn't get my slices of, oh, I did get my slices of 4. Okay, so how do I go about shading in 1/4? Well, 1/4 should be one of the rows, right? Because now I've sort of split it into 4 along the horizontal, but this one's already shaded in, so I can't just double shade it. I already ate that piece of cake, if you will, or whatever, right? So I'm going to have to shade in, you can still see 3 boxes. I just would shade 3 boxes in that aren't all along the same actual physical row to make sense of that. So here's 1, 2, 3. And if you count them up, what do you notice? It's 7. And the size of the pieces are now size 1/12, right? They're a 1/12 of the whole diagram. So that's where all those are coming. I'm actually ending up with 4 yellow boxes from my original 1/3. I have 3 boxes from the second one, which is 3/12, or 1/4, and I end up getting 7 individual boxes out that are all size 12. So that's where those pieces are all coming from, just so that you're aware. Okay, so we're going to do a couple of examples now. One that has unliked or like denominators, and then one that has unlike denominators. And any time that we get to the end of the problem, if we have the ability to reduce anything, we will. All right? That doesn't mean we have to change things into mixed numbers or anything like that. We're just going to reduce any factors that we have the ability to divide out or something like that. So if I have 1/3 plus 5/3, what will that equal? 6/3. And can I reduce? Absolutely. How can I reduce? Yeah, I can divide them both by 3. You don't necessarily have to show the dividing by 3 step, but you could. And then you have 2/1 or just 2. Okay, and if you want to jump just to the answer of 2 at that point, that's perfectly fine. So again, 1/3 of a cake plus 5/3 of a cake, which means more than a whole cake, gives me 2 whole cakes. These two are kind of like the one that I drew before. The fractions are different, but I do have the same denominators. I have 1/4 and 5/3. So I'll make a smile. I can actually do 1 times 3 is 3, plus 4 times 5 is 20, divided by 4 times 3, which is 12. This gives me 23 on top, 12 on bottom. Can I reduce it? This one doesn't work to reduce. So sometimes they reduce and sometimes they don't. It is perfectly reasonable to notice at this point that this is not a proper fraction, which is about what I'm about to define anyway. Mixed numbers are the sort of counterpart of improper fractions. They're used in everyday life to represent values that are an integer combined with a proper fraction, and a proper fraction just means that the top is smaller than the bottom. Mixed numbers are very helpful to visualize what's going on. If I tell you 5/3 of a cake, you might not have immediately thought of the fact that that means I have more than one cake. That might just not have been on the forefront of your mind. It just looks like this funny number, right? But if I told you I have 1 2/3 of a cake, you would immediately know that you have more than one cake. So there are direct applications that make mixed numbers more visually applicable to the things we see and work with in real life. They're not necessarily easy to manipulate with, which is sort of the counterpart of mathematics, is that they're not often easy to work with. But we can go between the two if we have a need to do so. So if I have the improper fraction 14/3, and I want to figure out, well, I've got 14/3 of a cake, which nobody would ever say, right? That sounds funny. But I have 14/3, and I want to know, well, how much is that in a sort of a picture that I can picture in my mind? I know it's more than 1, but how much more, or what does that actually look like? So we can actually take that and we can divide that. So I have 14, and I'm going to divide that by 3. So I've been working with my 6th grade children. They've been working on ratios and proportions and stuff, so I'm really curious as they go through this 6th grade block that they're in, and to see how closely they're going to line up with what we're doing in class this semester. They struggle to remember, and maybe some of you do too, or maybe you did, which number goes under the house. Y'all ever call it that? I don't remember ever hearing it called that, but my kids call it the house. So they want to know which number goes under the division sign. It's always the number that's on top. It doesn't matter if the number that's on top is smaller or bigger. So you have to keep that in mind, that your students may try to struggle with where the numbers go. And it's the one that's on top that always goes underneath the division sign. So how many times will 3 go into 14? It will go in 4 times. And 4 times 3 is 12. 14 minus 12 gives me 2. Now, there's lots of things that you could do once you get to this point, depending on what you're working with. My kids are working with decimals right now, so they keep going and try to get a decimal expansion about this. This chapter that we're working in is all about fractions. So our goal at the end of this problem is to write it in a fractional form. So what that means that I'll have is I'll have the whole number 4 that's on top, And this remainder tells me how much of the original 14 is left over. It's a remainder out of the original 3 sized slices of cake that I had, or whatever object you want to imagine. So this is equivalent to the number 4 2/3. 4 full cakes and 2/3 of an additional cake. So while we want to go from improper fractions into mixed numbers, we also want to go from mixed numbers into impartial fraction. Not impartial. Improper is the word I want. Improper fractions. And here's an example. Now, first, let me sort of warn you that the negative doesn't affect our operations of what we're doing. If the original number is negative, the improper fraction is also going to be negative. Okay, so I don't have to work with the negative. It'll just be attached to the answer at the end. So for the moment, we're going to ignore it. And we're just going to focus on the 3 5/8. Okay, so far so good? Just ignore the 3, the negative. We didn't get rid of it, we're just ignoring it. So again, this is one where there's a very nice visual. I'm going to show you the visual, and then I'm going to tell you why it works, because it kind of looks a little bit like magic. And I absolutely hate it when math looks like magic to people, because then they start to disbelieve that there's any sort of grounding or basis for what's going on. And there always is. It's just not always easy to see. So the visual is that we're going to multiply 8 times 3, and then we're going to add that to the 5. So we're sort of going around clockwise with multiplication and then addition. And we start with the denominator. This is where we start. So what is 8 times 3? 24, and 24 plus 5? 29. So I have 29 on top, and I have that same 8 on bottom. Okay, so the answer to the question is actually negative 29 over 8. Let me talk to you about why this actually works. The number 3 5/8 means 3 wholes plus 5/8. Agreed? 3 is the same as the number 3 over 1. Okay? And what we learned in the last little bit, a couple slides ago, is that if I have unlike denominators, I can cross and do a smile. So in other words, I can do 3 times 8, I'm going to actually write it out this time, plus 5. And that's exactly what this pattern up here does. It's the 8 that's on the bottom times the 3 over here plus the 5 that's on the top. That's what's happening. And then I have, of course, have the same 8 times 1 on the bottom, so I have the 8 on the bottom. If you don't like that visual, another way that you can think of it that might look a little bit more familiar potentially is you could think of getting the common denominator like this, right? So you still see that same 3 times 8 plus 5 all the way across the top, and now the denominators match, so you make them an 8 on bottom. So that's why it's working. I don't care what method you use to do that. It doesn't matter to me. But there is, I feel like the first one that I showed you is the shortcut kind of way of doing it. But certainly the other ones are perfectly fine as well. Theorem 6.6 is the additive inverse property. In Chapter 5, for those of you who've had number theory, you learned about inverses. Inverses for addition are the value that you add to something to get back to 0. So the inverse of 2 is negative 2. It's the additive inverse. They add together to give you 0. It works the same way for all rational numbers, a over b. So if I have a rational number a over b, then there is a unique rational number that's negative a over b. So that when you add them together, it becomes 0. Along with that additive inverse property, there's the additive property of equality. And what it says is that if we have the number a over b and c over d, that if I add the same value to both of them, I should pause just a second, if those numbers a over b and c over d are equal to begin with, and I add the same number to both of them, I will get the same equality to begin with. For example, if I stood at the front of the room, and we won't do it because then somebody'd have to get out of their chair, and somebody who was exactly the same height as I stood next to each other, we were equal in height, and we both put on 3-inch heels, we would still both be equal in height. right? You increase both of our heights by 3 inches, the equality stays the same. And that's all the additive property of equality says. So where do we see these two properties used? Well, we see them used extensively in solving equations. And in fact, you use them so readily that you probably don't even recognize that you're using them when you do. So I'm going to show you how you can kind of think about that and mention it when I do it. So hopefully you're aware that you're using it, even if you can't always think about, or you don't always think about when it's being used, that it's being used frequently. So we're going to do an example with some mixed number addition. And there's actually two different ways of solving this problem in terms of computation. But let me make mention with you real quick that this problem is an exact application of the last two properties. So when we're solving an equation, our goal is to get x alone, right? Yeah. So whatever's next to x, we look at it and we say, hey, look, it says minus 2.5. So what I do is I ask myself, what's the additive inverse of 2.5? You may not say those words, but that's what you're asking yourself. You're saying, oh, look, it's positive 2.5, right? That's the additive inverse property. How did I come up with 2.5? Well, because it's the additive inverse of negative 2.5. Not only that, but when you do that, the fact that these two add to 0, these two values, thinking about moving straight down, but these two values add to 0, that's also the additive inverse property, right? It becomes 0. That's the whole reason we want to do that. And our ability to add the 2.5 to the left and add the 2.5 to the right simultaneously is the additive property of equality. So all there in one step is two different properties that you may not even be thinking about at all when you're actually doing the problem, but they're there. Now, the answer to this question is actually whatever the answer is to 3 1/3 plus 2 1/2. So we'll come back and we'll write down the answer underneath it in a moment, but I want to show you two different ways to solve the problem. So one method, here are two methods. So the first method I'm going to show you is the way that I learned to do it. It's improper fractions. And I'll just preface right now with the fact that this is what I learned. I'm very familiar with it, but it is not the one I choose because I think the other method is actually easier. So this, and it doesn't matter to me again which one you use either. There have been cases where I've asked people to show me both or to show me one specifically. So you do need to know both of these particular methods. But let me show you how it works. So we're really just trying to add the number 3 1/3 plus 2 1/2, right? So improper fractions says I change both of these into improper fractions. So I multiply and I add. So 3 times 3 is 9 plus 1 is 10. So I have 10/3 here. And then over here on this one, 2 times 2 is 4 plus 1 is 5. So then I have 5 over 2. And then I use addition of improper fractions, right? I use addition of fractions with unlike denominators. So I would do like this, and I would say, okay, I've got to do 10 times 2, that's 20, plus 3 times 5 is 15, over 3 times 2 is 6, or some variation of addition of fractions. There's a couple other ways you can think about it, but this is what your book shows us, so I'm going to stick with it. What's 20 plus 15? 35. I almost said it. Now, I mentioned last class period, or maybe even the very first class period, that generally speaking, there's no reason to move in and out of mixed numbers unless there's a hearkening reason to do so, unless somebody tells you to. So here's I'm telling you to. If the problem starts out with mixed numbers, your answer is going to be in mixed numbers. So this problem needs to go back into mixed numbers because that's where the problem began. So we're going to take 35 and divide by 6. How many times will 6 go into 35? 5 times. 5 times 6 is 30, and I subtract to get 5. So the whole number on the top is 5. I have 5 as a remainder out of the original sized 6 pieces, sized 1/6 pieces. So the answer to this question over here is 5 5/6. And this is one way to show doing that. Okay, so I realize that I just shifted things that are now not lining up on the left, but I need some more space, so we're just going to do it anyway. All right, the second way is, how many of you are familiar? You've seen that way before? Show me your hands real quick. Most of you have. Is that the only way you know how to do it, or are there others? Is there another way that some of you have learned? Emma?
I vaguely remember somewhere along the road where my teachers have said, worry about the whole numbers and then the fractions and then you put them together.
Yeah, and that's the other way we're going to do it. Yeah, so the second way I think is actually easier usually because it keeps everything smaller. One of the sort of inherent problems with the improper fractions is that I end up with numerators that are quite large and maybe even larger than that. I mean, like, that's not even terrible. So one option here is, or the second option is basically what you were just describing, Emma. And so what we would do is we would sort of piece these together differently. So again, I had 3 1/3 and I have 2 1/2. And what I would do is I would separate them. I would put the 3 and the 2 together because it's 3 holes and 2 holes. And then there's a 1/3 and a 1/2, and I put them at the end. Okay, not because it's beginning and the end per se, but because I'm grouping whole number pieces together, I'm grouping fractional pieces together. So the 3 and the 2, of course, is 5. And then over here, I do the same thing that I did before. I just have smaller numbers I'm doing it with. So I have still the plus sign here. I have a 2 times 1 is 2, a 3 times 1 is 3, over the 3 times 2, which is 6. So this ends up with 5 5/6. And there's still a chance at this point that when I did the 2 plus 3 on top that I actually end up with something that's improper that I have to change to. It's still going to be smaller than the 35/6 that I had on the last part of the problem, doing it the other way. So those are two specifically different ways to do it. I call this, I didn't give it a header, maybe I'll shift mine down and you can put yours in. I call this the mixed number approach because I'm actually leaving the numbers mixed instead of making them all into improper fractions. Yes?
When we're adding fractions with the uncommon denominators, do you want us to do the whole cross and smile thing?
You don't have to, but you got to show me something.
Right.
Yes.
So I can, like, find the common
yes.
denominator. Okay.
Exactly. So if instead you decided that you were going to show, like on this one, we'll just use this one as an example. There's 1/3 plus 1/2, and you decide, oh, well, I'm just going to put a 3 here, and I'm going to put a 2 here. You could do that. That would be another sort of version of showing me. You got to show me something.
But on the test, like, you're not going to, like, say, okay, you have to show me this way to add them?
No.
Okay.
Not with addition of fractions. This is just something that your book does that's kind of nice. It works super nice when the two denominators are completely different.
Right.
When the two denominators have something in common, it's a little bit overkill because you might end up getting something larger than you needed. So, yeah. Okay, you know what? So then we're about to switch into the definition of subtraction. So I think I'm going to just pause right here and we'll pick up here next time. We'll get caught up eventually. So I'm not too worried about that. I would like for you to have a chance to make sure that you've thought through and moved through how we do group work fully. So we'll pause here for today and I'll change the due date on the 6.2 to next week, or to Wednesday of next week.